The last section is section 6, Galaxies and the Expanding Universe. This is the distribution of galaxies in the universe. Okay, we know that we have these giant clusters of rotating stars called galaxies. And these galaxies are grouped into clusters of galaxies. They're called galaxy clusters. And then these clusters of galaxies are grouped into larger clusters called superclusters. So that's basically the due to the expansion of the universe, the light received from some galaxies is redshifted. And the reason for that is that it's like a Doppler effect. As an object moves away from us, as an object recedes from our line of sight, then the wavelength becomes shifted towards the red part of the spectrum. The reason for that, we understand, is that space itself is expanding. Not that the galaxies themselves are moving away in a static space, but the space itself is actually expanding with time. But the formula works pretty much the same as the Doppler effect. So a shift in spectral line from the galaxy emission spectrum is given by delta lambda is equal to lambda prime, which is the new value for lambda, the observed value, minus the original value. And so that gives us delta lambda. So delta lambda, which is the shift in wavelength divided by the original wavelength, will be the same as the ratio between the velocity of light divided by the velocity of the galaxy divided by the velocity of light, the speed of light. And that gives us the speed or the velocity of the galaxy. Okay, explain the redshift of light from distant galaxies. So this is what we have. We have absorption lines from our sun, so we're not moving relative to the sun, it stays a fixed distance from us. We look at galaxies which are a supercluster BAS 11. We notice that these wavelengths, this particular absorption line, is shifted to a slightly longer wavelength. And we basically apply the Doppler shift equation. We find that that must be going at a speed of 0.07 c. In other words, 7% of the speed of light, because the wavelength has been shifted by 7%. State Hubble's law. In the 1920s, there was an astronomer called Edwin Hubble. He noticed that some galaxies were blue shifted. Okay, but they tended to be quite close. So there's a random motion of galaxies. Some are moving towards us, some are moving away from us. So that ones that were near us, some were moving towards us, some away from us. So there's a random variation in the velocities. However, most galaxies, especially the further away they went from us, were more and more redshifted. The further away they were from us, the more redshifted they were. And therefore, the further away from us that they were, the faster they must be moving away from us. In fact, there was a fairly linear relationship in that if it was twice as far away, it was actually moving away from us at twice the speed. So he basically plotted a graph of the recessional velocity, which is going to be in kilometers per second, against the apparent distance in megaparsecs, in millions of parsecs. And he basically plotted this recession speed versus distance. And he ended up with pretty much a straight line through the origin. So what does that tell us? It tells us basically that the recessional speed, recessional velocity, is proportional to its distance. This is basically the equation for a straight line, but of course the intercept is c, which is equal to 0. So y is equal to mx. We have to think about in terms of the y, which is the recessional velocity, is proportional to the distance away from us. So we can put it in this sense. V is the recessional velocity, is equal to the distance away from us times by h, which is the Hubble constant. The Hubble constant what is the gradient of this graph? And that's going to be the Hubble constant. This is the value for m. So it's the rise over run. So it's the number of kilometers per second divided by the number of megaparsecs. So we can find the gradient of this graph. Go from 0 to 25,000 divided by 400 megaparsecs, and we find a value of approximately 60 kilometers per second per megaparsec. And this is roughly the value for Hubble's constant. So basically the recessional velocity is proportional to the distance away. So v is equal to hd. V is a velocity in kilometers per second. H is Hubble constant, which is roughly 60 kilometers per second per megaparsec, and d is a distance away from us in megaparsecs. We need to know about the limitations of Hubble's law. I said the value for about 60. Now the problem is there are great uncertainties, 20% or so, 30% in measuring such large distances. Think about how can we measure large distances? Well, the light is very faint by the time it gets to us, and it's not a very precise way of measuring. For example, we use a spectroscopic parallax for galaxies that are close to us, but the ones that are furthest away, we have to use the method of looking at these standard candles, Cepheid variables. So here we have it. So we know that the recessional velocity here on the y-axis is proportional to the distance away. The limitations, the distances are not easy to measure. The uncertainties are too great. There are difficulties in locating Cepheid variables, those distances, and of accurately measuring their luminosities and therefore their distance. For example, we have a value here which is roughly 15,000 kilometers per second, and it's this point here, but there's rather a large uncertainty in the apparent distance. So we have this horizontal error bar, uncertainty bar, which is quite considerable, and it gives us two values for the gradient, two values for Hubble's constant, and it goes from basically 55 kilometers per second per megaparsec to 75 kilometers per second per megaparsec, all because we can't measure the distances accurately enough. So the expansion of the universe. We now understand that the universe is expanding. We look at the galaxies that are twice as far away from us, and they are going twice as quickly. If we know the distance d and we know the velocity, we can work out the speed that they're traveling at. If we run that backwards, we can assume that they all basically started more or less at the same point and at the same time. Explain how the Hubble constant may be used to estimate the age of the universe. Now, this is a picture of what the universe is now. This is the time now, and this is the distance. So we take a distance in space, could be from our sun to the nearest star. This is going to be the distance, and this is where we are now. So we take a galaxy with a recession velocity v. Well, we'll take that, and we can find out its distance from us. Now we're assuming a constant expansion of the universe. If we go backwards, we can work out, if we know the velocity, we know the distance, we can work out the time that it took to get there. So in other words, we can find out the age of the universe. Now, if we know the velocity and we know the distance away from us, we know how much time it took for that galaxy to get to that point. So in other words, we know when we were at the same point as this galaxy. In other words, how long ago the Big Bang happened. We also know that v is equal to hd. This is with Hubble's constant. So we equate those two. So d over t, which is a distance divided by time, the distance away from us, divided by the time, which is the age of the universe, is equal to hd. H is Hubble's constant, d is a distance away. We can simplify that again, divide both sides by d, and we end up with 1 over t is equal to h. So in other words, h, the Hubble constant, in a strange way, is the reciprocal of t. In other words, age is the 1 over the age of the universe. We've got a problem with units, however, because the Hubble constant is in kilometers per second per megaparsec. So we have to convert kilometers per second to meters per second, and we have to change megaparsecs to meters. Okay, and we will look at a problem like that later on. So 1 over h is equal to t also. Now, there are a few problems. We're assuming, of course, that the universe is expanding at a constant rate. And a value for t is equal to 15 times 10 to the 9. See if you can find out, do 1 over h and convert it into meters and seconds and so on, and see if you get a value for t. You should end up with a value like this. But that assumes a constant expansion rate. But what happens if the expansion is slowing down? We're at this point here. So how is it possible that we could be here and the expansion rate is slowing down? In other words, we must be following a curve which starts here and is expanding, and this expansion is getting less with time. But that would mean that our estimation for the age of the universe was actually shorter. So in other words, this value of the age of the universe depends on a constant expansion rate. If the universe is expanding and is slowing down, the universe is actually going to be younger than we apparently think it is now. That's if the expansion is slowing down. On the other hand, what happens if the expansion is speeding up? The only way we can be in this position and for it to speeding up, in other words, this line is going to curve the other way, is to start at this point, and then it's speeding up and expanding faster and faster and faster with time. It means that the universe must be much older than it is now. That it was a much longer time ago that it started, because it's getting faster and faster and faster as it expands. Right, a past paper, November 2004. One of the most intense sources is this galaxy. We know that it lies about 1.5 times 10 to the 7 light years away from the Earth. A possible value for the Hubble constant is 60 kilometers per second per megaparsec. So we have to use this value to estimate the recessional speed of this galaxy. So I want to try that now. You should end up with an answer of 300 kilometers per second. You can pause, and otherwise I'll go through the solution. We know that the recessional speed is related to the distance that we know by v is equal to hd. We know the value for h, we know the value for d, so we need to find v. So we also need to know that 1 light year is 9.46 times 10 to the 15 meters, and 1 parsec is roughly 3 light years. So the value h is 60. And the distance, what's the distance away from us? We know it's 0.5 times 10 to the 7 light years. But we want to find out, basically, what is the distance in megaparsecs. This distance only works in megaparsecs. We know it in light years. So we have to divide by 3.26. But that just divides by the number of light years in a parsec. We need to divide by 3.26 times 10 to the 6 because it's number of megaparsecs in that distance. So that you calculate this, and you'll end up with a value of 300 kilometers per second, hopefully. Now the age of the universe, we know that t is equal to 1 over h. And as I said before, you need to do this calculation, and you should end up with a value of 5 times 10 to the 17 seconds. Time, or the age of the universe, is 1 over h. H, we know, is 60 kilometers per second per megaparsec. So we need to find 60 kilometers per second in meters per second, and we need to divide it by number of meters in a megaparsec. So basically it's going to be 1 divided by h, where it's 60,000, because this is the value for number of meters per second, 60 kilometers per second, and divide by the number of meters in a a megaparsec. We know there are 9.46 times 10 to the 15 meters in a light year, and we know there are 3.26 times 10 to the 6 light years in a megaparsec. So you do this and you end up with basically this calculation, and here you should end up with a value for 5 times 10 to the 17 seconds. Do this. Learn how to do this calculation by yourself, because they are asked this question so many times.